We are going to use this example to demonstrate how we read the data and write the data. Please remember one thing, a general guideline. Okay? Scientific measurements are reported so that every digit is certain except the last one, which is estimated. In other words, if I have a data here, 5.213 gram, okay, when you have this data, the 5, 2, 1, those three digits are accurate, okay, or are certain. But the last digit, 3, is uncertain. It's from our estimation, okay. One way to reflect this uncertainty is to write the data as 5.213 plus minus 0.001 gram. Okay, so this 0.001 part represents the uncertainty of the data here. Okay, another angle to look at this problem is you can write the data as 5.212 gram to 5.214 gram. In other words, the true value of this object is in this window right here. Okay. Chemistry, we usually use the first way to record our data. It's simple and it's easy. All right. Now, we understand the basic guideline for us to read the data. Now, let's use this example, okay, the graduate cylinder. You have certain amount of water in this graduate cylinder. How do we read the data? Remember, when you read the data in the graduate cylinder, you have to pay attention to one thing, and that is the meniscus curve of water. Okay, you have to read the data based on the bottom of the meniscus curve. Okay, now how do we read it? Okay, then you have to pay enough attention to the markings of this graduate cylinder. Okay, let me mark it. For this one here, it's 4.0 ml. The unit is ml. Okay, and this one here is 5.0 ml. Okay, now between 4 and 5, there are 9 markings. Okay, that means that each mark represents 0.1 ml. Okay, so for this one, it's 4.1 ml. Okay, then the next one 4.2, next one 4.3. Now you can see from this picture, the bottom of the meniscus curve is between this line and this line. This line here represents 4.5 ml. Okay, and then this line represents 4.6 ml. In other words, the bottom of this meniscus curve is between 4.5 to 4.6 ml. Okay, 5 and 6, they are certain because they are markings on this graduate cylinder. Okay, so next thing is we have to give it an estimation of the bottom of the meniscus curve because it's between 5 and 6. How do we do it? We just mentally divide the space between 4.5 and 4.6 by 10 and then give it an estimation. According to my eyes, the bottom of this meniscus curve is closer to 7 or 6-ish. So I would like to read that as a 4.57 ml. Okay, so the data here, 4, 5, they are certain. 7 is from my estimation. Okay, You may ask me, how about I read the data as 4.5 or 6 mil? It's okay. Okay, it's okay. Different people will have slightly different estimation. It could be a little bit different, but certainly if you read the data as 4.67 mil, that's not correct, because we know that this meniscus curve is below 4.6 mil, so it should be lower than 4.67 mil. So this one is not correct. All right. Now, on your right side, there are two balances. Okay, so one gives you the mass of this chemical as 10.5 gram. Again, 1, 0, they are certain. 5 is an estimation. Okay, we didn't do the estimation. The balance did it for us. Okay. The second balance here, as you notice, it's more precise because it has more digits. Okay. And again, the 10497, they are certain, but the last digit is an estimation. Again, balance did that for us. Okay, so that's why everybody loves digital instruments, because it saves your time a little bit, but we do have to know how we estimate the last digit if you have to manually record your data. All right, now next slide, let's do some practice. Okay, again, this is a graduate cylinder with a certain amount of water in it. Well, according to my eyes, the meniscus curve right here is right above this this line here. Okay, and now let's read the data. For this line, it's 20.0 mil. You may ask me, how do you know it has 1 decimal place? Well, let me tell you. You have to consider the line below this, the longest line, and the line above this longest line. Okay. If you remember what we did in the previous slide, for this one here, 20 labeled as 21. Okay. And this line labeled as 20. And between the 21 and 20, there are 9 markings. Each marking represents 0.1 mil. In other words, this is 20. Well, this is a burette. Okay, this is a burette. Well, it looks like a graduate cylinder, but if you compare the two, you will realize that the range of the markings are slightly different. Okay, but anyway, the idea or the mechanism or the principle that we need to follow is the same. Okay, now this is a burette, and this is water level here. Again, you have to pay attention to the meniscus curve. Okay, according to my eyes, it looks like the bottom of the meniscus curve is right on this line here. Okay, so let's read the data. Well, for this one here, this line, that is going to be 20.0 mil. Okay, one question you may ask: how do I know it is 1 decimal place? Well, let me tell you. Between 21 and 20, there are 9 markings. Each marking represents 0.1 mil. Okay, so for this line right below the 20, that is going to be 20.1 mil. Okay, this marking represents 20.1 mil. All 3 digits are certain. And for this line here, you may not be able to see it right here, okay, right here. The rating should be 19.9 mil, because between 19 and 20 there are 9 markings. Each marking represents again 0.1 mil. All right, again 3 digits, they are certain. Now that tells us for this line it has to be 20.0 mil. That's how I know it has 1 decimal place. Okay, now as I mentioned a moment ago, according to my eyes, this line is right on this 20.0 mil line. So 20.0, these 3 digits are certain, but I still have to give it an estimation. Okay, so since it's right on the line, I'll give it as 0. That's my estimation. Of course, if you read that data as 20.01 mil, okay, or 19.99 mil, both of them are fine. Okay. Now, let's take a look at the second example. It's about the thermometer. Tells us the temperature, the degree Fahrenheit. Okay. Again, we follow the same guideline. Okay. Well, 110. Between 100 and this one actually would be 110. Okay. So between those two markings, there are 9 smaller markings. Okay. Again, so each marking again represents 1 degree Fahrenheit. Okay. So that tells us for this line here, that represents 1, 2, 3, 103 degree Fahrenheit. Okay, for this line here, that represents 104 degree Fahrenheit. Okay, so I can get the 3 certain digits as 103 because this mercury level is right between 103 and 104 degree Fahrenheit. So 103 are certain, 10 and 3, these 3 digits are certain. Okay, I still have to give it an estimation. According to my eyes, the top of this mercury is probably closer to the 103 line. So my estimation would be about 3. Okay, so that's my estimation. Of course, again, if you read that as a 103.4 degree Fahrenheit or 103.2 degree Fahrenheit, both of them are fine. Okay, so this is data rating. Now let's take a look at this slide. This slide tells us some very important concepts. Okay, the first 2 we're going to talk about are precision and accuracy. Well, precision means how close the values are to one another or how reproducible they are. Accuracy is about how close the measured value is to the true value. Let me use a specific number to explain it. For accuracy, okay, let's see. Do you happen to remember the 2 balances we had a moment ago? One balance gives you 10.5 gram. Okay, the other one gives you 10.4977 gram. So which one is more precise? Well, it depends on how many decimal places the data has. The more decimal places you have, the more precise the data reading is. Okay, so when you compare this to this one, apparently is more accurate, is more precise because it has more decimal places. All right, this is how we decide the precision. How about accuracy? Again, let's see if you have 2 data rating. One is 5.72 meter. Okay, the other one is 5.75 meter. And if you know the true value of the object should be 5.74 meter, Okay, so this is a true value. Now, when you compare the two readings, apparently 57.5 meter is closer to 5.74 meter. Okay, so that's why we will see that 5.75 is more accurate than 5.72 meter. So that's how we distinguish precision and accuracy. Okay. Now, the next two concepts that we are going to talk are random error and systematic error. Okay, we have to use this example to demonstrate these two different types of errors. Let's see. In this example, there are 3 students, and then they collect the data here. Okay, this is a student A, student B, student C. Each one of them did 4 trials, and the bottom row here is the average mass. Okay, by looking at this table, it may not tell you too much, but it would be quite obvious if you take a look at this column diagrams for each student. For student A, okay, so here you have 4 columns. B and C seem the still 4 columns. But if you take a closer look, for student A, 2 of them are higher than the true value, true mass of this object. Okay, the true mass is 10.00 gram. Okay, and the other 2 ratings from student A are lower than the true values. Okay, for student B, all 4 values are lower than the true values. For student C, again, 2 of them are slightly higher, and the other 2 are slightly lower. Okay, so how do you evaluate this 3 students by using precision and accuracy? Okay, we have to discuss that first. Well, for student A, as you notice that 4 data points, they are not that very close to the true mass. Okay, so they are not accurate, and all 4 of them are quite different from one another, so they are not precise. So the conclusion is inaccurate and imprecise. For student B, all 4 values are close to each other, so they are precise, but all 4 of them are, quite further away from the true value, 10 gram here, okay, 10.00 gram. So they are not accurate. All right, so for student B, the data is inaccurate but precise. While for student C, okay, all 4 data, they are close to each other. Okay, so they are precise. Okay, and they also very close to the true value, so they are accurate. Okay, so the evaluation or the conclusion would be accurate and precise. Okay, now one thing you probably notice is something is missing here. All right, so let me challenge you. Is that possible for us to get a situation like accurate and imprecise? Okay, you can pause for a few seconds and then resume the video. Is that possible for us to get the accurate but an imprecise situation? Well, the answer is no. Well, you think about it. If all of the data readings are accurate, that means they are very close to the true value. Okay? If they are close to the true value, they should be close to each other. Right? It's sort of like, both you and me are living very close to Walmart. Okay? If we are talking about the same Walmart store, we are living very close to this Walmart store. That means we have to live very close. Same idea here. Okay, it's not possible for us to get a situation that is accurate but imprecise. That's not possible. Okay. Now, let's continue our discussion about random error and systematic error. Random error is the errors that have equal probability of being too high or too low. Well, this can be reflected by student A. You can see that two of them are higher than the true value, two of them are lower than true value. So it looks like a random, does not have a pattern. Okay. Now, for student B, it's different. Okay, it's about the reason for the the student B is about the systematic error. Systematic error is the errors tend to be either too high or too low. As you notice that 4 data points, but all 4 of them are lower than the true value. Okay, so this is caused by the systematic error. Okay, so how do we deal with the random error and the systematic error? Well, for random error, you have to repeat the experiments multiple times and take the average. Okay, so by doing this, you can sort of like cancel the random error among the different readings, and then you can get closer to the accurate value. How about the systematic error? Well, in order to remove the systematic error or minimize it, you have to calibrate your instrument carefully. Okay, for instance, if you are using a balance, it might be better if you can calibrate your balance by using a 50 gram of weight. Okay, before you start your experiments. Okay, so in order to make sure that this balance is function properly. Okay. All right, this is the reliability of measurement. Okay, let me know if you have any questions.